Hey everyone and welcome to Toppscholars. Today we are going to study relations and functions. So the entire chapter we are going to discuss in this. What exactly are we going to study? We'll study what are relations. Then we are going to see what are different kinds of relations. Then we will see what are functions. We'll also see what are different types of functions. We're also going to see how to find out the inverse of a particular function. And then we are going to have a lot of problems in this session. So let us begin. So to start with, firstly, if you look at the first word here, that is relation, right? What exactly is the meaning of relation? You know what is relation, right? So if I ask you the relation with your father, so that's a father and son relation. With your mom, that's a mother and son relation. Or maybe if you are a girl, that can be a father and daughter relation, mother and daughter relation. Is that only it? No, there are so many relations in this world, right? It can be a relation of friendship. It can be a relation of mentorship, a coach. It can be anything. So we are going to talk about relations and then how those relations and functions are connected. That also we are going to see, and we're also going to understand what exactly is function. So firstly, without wasting much time, let us understand what is the meaning of relation in mathematics. In real life, we know what relations are. When it comes to maths, we talk about relation when we have two different set. I hope you have studied in the chapter of set and you remember what a set is, right? A set is nothing but a well-defined collection of objects. So when you have well-defined collection of objects, that is called as a set. But when we talk about relation, how is it connected to set? That we'll try to understand. So a relation in mathematics defines a connection between two sets. It defines the connection between how many sets? Two sets. Now those two sets, they can be different. They can be same also sometimes. You'll get to know in the questions. So suppose if I have two different sets and here it is. So let us consider when we have two different sets A and B, a relation from A to B. How do we read this? A relation. Generally, the relation is denoted by R. Generally, a relation from A to B is a subset of A cross B. I hope you remember what is the meaning of subset. So firstly, make sure that your concept for the chapter of set are also clear. The chapter as in you must have already studied about set in your 11th grade as well. And I'm assuming that you know the basics of set. Okay, so a subset. I'm sure you know what is a subset. For example, if I have some elements in A, say 1, and if I have some elements in B, say 1 and 2, then here I can say that A is the subset of B. Just to make you a quick recap. So a relation R from A to B is a subset of A cross B. So forget about this. R is what? This relation R is a subset of whom? It is a subset of A cross B, that is the Cartesian product of A and B, right? Okay, so have a look here. Let us try to understand. A simple question. Two sets are given. Set A, the elements in the set A are 1, 2, 3. The elements in the set B are 5, 6. Then we are supposed to check whether this particular set, this is again a set, right? This is a set of ordered pair. Suppose this set is set R. We are supposed to check whether this set R is a relation or not. So we'll say relation exists when R is a subset of A cross B. So firstly, our main task is what? Our task is to find out A cross B, right? Once we find out A cross B, then we will check whether this particular R is a subset of A cross B or not. So, firstly, try to understand this. The two different sets are set A. The elements in set A are 1, 2, 3. Where is this coming from? It is coming from here, right? And then set B. It has the elements 5 and 6. Clear? This is A, this is B. We are supposed to find out the Cartesian product. A cross B means what? The Cartesian product of A and B. Correct? So what we do is, we just take the ordered pair. That is, we'll combine 1 with 5. So 1 comma 5. 1 with 6. 1 comma 6. 2 with 5. 2 comma 5. 2 with 6. 2 comma 6. I know you already know how to find out the Cartesian product. This is just a recap of it. So 3 comma 5. 3 comma 6. So this is what? This is A cross B. So how many ordered pairs are there in A cross B? You can check. 1, 2, 3, 4, 5, 6. There are 6 ordered pairs in A cross B. Now tell me one thing. What is our set R? We are supposed to show whether this relation exists or not. So this R has to be the subset of A cross B. So check. 1 comma 5. Do we have 1 comma 5? Yes. 1 comma 6. Do we have 1 comma 6? Yes. 2 comma 5. Do we have 2 comma 5? Yes. 3 comma 6. Do we have 3 comma 6? Yes. We have everything here. That means definitely the relation exists. So this is a relation because R is a subset of A cross B. Now if in this I had something, say 10 comma 15, this is just an example, then will this be a relation? Definitely no. Can you see 10 comma 15 here? 10 comma 15 is not a member of A cross B. So we cannot say that the relation exists there. So simply what we need to understand and identify is that R should be a subset of A cross B. Okay. Now understand one more important term here. In fact, 2 important terms here. Now suppose if I take the ordered pair. So here is my ordered pair 1 comma 6, right? So this ordered pair I have picked up. Always remember the first element, that is 1, is called as the domain, the first element, and the second element is called as the range. So indirectly I can say that if I have A comma B, so this A is nothing but our domain and B is nothing but our range. So please make a note of this. They might ask you some questions based on domain and range as well. So don't worry. I hope this part is clear to you, and let's continue further. Okay. Now let us have more examples of relations basically. So example is, let A be a set of students in class 12, right? So A is what? Set of students of which grade? Grade 12. And B is the set of students in grade 11, right? So we can say that we're trying to create a possible relation basically. So a possible relation R. So R is a relation from A to B, right? R is a relation from A to B. What is A? A is a set of students of class 12. What is B? B is the set of students of class 11. So the relation could be something like this, that A is the mentor of B, right? Class 12 students, they are like a guide to the class 11 students, right? So we can say that A is the mentor of B. Is it the only relation possible? You can have multiple relations here. Class 12 students, they are generally, I can generalize this, that they are elder than class 11 students. So we can have one more relation, right? That is R is a relation from A to B, that is from class 12 students to class 11 students, such that the age, I'm talking about the age, such that A, class 12 students are going to be more in age than class 11 students, right? So A is greater than B. This is just an example to make you understand. There can be ample of relations here. So that's how we write down R is the relation. And one more thing very important here, that this A is an element, right, which belongs to the first set, that is capital A. And B is also an element which belongs to the other set, that is B. So this is what we are supposed to remember. Okay. Now let us have the mathematical representation. So formally, a relation R from set A to set B, we have already discussed this. A relation R from set A to set B is a subset of A cross B. Now, very important, if A comma B ordered pair belongs to R, then A is related to B. A is related to B. Mathematically, we write it as A. R is the relation A related to B. So the first and second elements, they're related to some other, in some or the other way. Okay, so A related to B, you can see here as well. Now, we can have more examples of relations. There can be many. Sibling relations, we discussed that in the starting also, right? That is, R is a set of ordered pair A and B such that A is a sibling of B. That is, A can be brother of B, A can be sister of B, B can be brother of A as well, depends. And it depends on who A and B are, right? Then, not necessary only will have sibling relations, we can have friendship relations. Two friends, A and B are two friends, so we can say that A is the friend with B. So that is also a relation. Age comparison, we took this example, right, in class 12, class 11 students, that A is older than B. We can also have A is younger than B. That depends completely what A and B is. Okay. Now let us move on to a question based on relation. I hope this concept up to now is clear to you. So here is the first question. The question says, if R is a set of ordered pairs A comma A cube, where A is a prime number, please read the question carefully, A is a prime number less than 5, okay, A is a prime number less than 5. So this R is a relation, they are saying that this R is a relation, okay. Then find the range of R, we are supposed to find the range of R. I hope you remember one example where we talked about the domain and the range, right, the second element. So exactly that is what asked in this question. So here, if you notice very carefully, we can say that R is a relation and the ordered pairs are A comma A cube, but there is a condition for A. What is the condition? The condition is that A is a prime number less than 5. Now tell me, what all are the prime numbers less than 5? Can I say 2 is a prime number less than 5? Can I say 3 is a prime number less than 5? Isn't it? 2 and 3. Okay. Now, how is the ordered pair? The ordered pair is A comma A cube, right? So, we are already given that R is a relation where A is a prime number, A is a prime number less than 5, and this is A comma A cube. So, let me just make this as A cube, alright? So, A comma A cube. So, can I say 2 and 3 are the prime numbers less than 5? Yes. So, if I take A as 2, can I say this will become 2 comma 2 cube? That is my first ordered pair, and my second ordered pair will become 3 comma 3 cube. So here we go. We can take the values 2 and 3. Then we will have 2 comma 2 cube, 3 comma 3 cube. 2 will remain as it is. 2 cube is how much? 2 cube is 8. 3 cube is how much? 3 cube is 27. Now observe, in this set R, we have two ordered pairs, right? Which are the two ordered pairs? 2 comma 8 and 3 comma 27. So this element, as I told you before, if we have A comma B, then this is our range, right? So can I say 8 and 27? 8 and 27, right? So put a curly bracket here. 8 and 27, these two elements are the range of the given relation. I hope this is clear. 8, 27. Simple. Let's continue. Now let us try to understand different types of relation. The empty relation. Let us try to understand the definition of empty relation. It says a relation R in a set A. A relation R in a set A is called an empty relation if no elements of A are related to any elements of A. So, if the elements are not related at all, then we say it is an empty relation. right? Now suppose, I'll give you a simple example. If I have a set A, and then if I have the elements 1, 10, 15, and then if I define a relation, I'm defining a relation R on set A. I'm defining a relation R on whom set A. So R is always an ordered pair, okay? Such that I have A comma B, and then A is equal to B square. A is equal to B square. Now, this is a relation that I am defining. Now check, 1, 10 and 15. Is 1 a square of 10? No. Is 1 a square of 15? No. Is 10 a square of 1? No. Is 10 a square of 15? No. Is 15 a square of 1? No. Is 15 a square of 10? Any combinations you take, doesn't matter. You're not going to get A is equal to B square. None of the numbers there. If you pick one number and you square it, you're not getting any other number. So definitely this is empty, no? Such relation does not exist in A, right? So that is an empty relation. So in your house, maybe some of your friends come in, and if I talk about family members, is that person a member of your family? Is your friend, of course, you might consider him, but actually is not the member of your family. So there is no relation when I talk about family relation. So that is an empty set kind of, because he's your friend, right? He's not your family. So just a random example of real life. So here it is. How do we denote this basically? So we denote R as empty set. You can call this as empty set, you can call this as null set, doesn't matter. So let us see an example. So A is a set, and the empty relation can be expressed as R is a null set. That means if R does not contain any ordered pair, right, then we can say that it is an empty relation. Now let us talk about the new one, that is universal relation. Universal. Now universal means what? When the relation exists, firstly it should exist and it should be equal to all the elements of A cross B. So if the relation exists also and it is equal to all the elements of A cross B, then we can say that it is an universal relation. So a relation R in a set A is called a universal relation if every element of A is related to every element of A. So formally we write it like this: R is equal to A cross A. Even if you have two different sets, say for example set A and set B. So R is a relation from set A to set B. And if you want a universal relation, then R generally is a subset of A cross B. But if R is equal to A cross B, then we can say that the relation is, that particular relation is a universal relation, right? Okay. So A cross A. Example. So A is 1, 2. Firstly find out A cross A, right? So what will be A cross A here? Can I say it will be 1, 1, 1, 2, right? Then 2, 1 and 2, 2. This is what? This is your A cross A. That is the Cartesian product of A and A. Now tell me one thing. If I define a relation R like this, I am taking R as 1, 1, 1, 2, 2, 1, 2, 2. Now see 1, 1, here we have in A cross A. 1, 2, we have in A cross A. 2, 1, we have in A cross A. 2, 2, we have it in A cross A. Now can I say this R and A cross A are equal? So whenever they are equal, this relation is a universal relation. Simple. Although you are not going to get much questions based on this, but you need to know what is an empty relation, you need to know what is an universal relation. Now comes an important one later, so please try to concentrate. So here every element is related to every other element including itself. So obviously including itself as in 1 and 1, 2 and 2. Okay. Now let us talk about reflexive. Reflex, right? Reflex means what? With something that comes back, or when you say you look at the mirror, that is like your reflex, you versus you. Same thing. That is reflex, right? So we can say that A relation R in set A is called a reflexive relation if every element is in A is related to itself. If every element in A is related to itself, that is a reflexive relation. So, it looks like this. The set of ordered pairs A comma A that belongs to R for every A belonging to A. So, A comma A, that means the same thing. You can have an example like this. Suppose A is a set of 1, 2, 3. Now, even if you take the Cartesian product A cross A, you get 9 different elements, 1, 1, 1, 2, 1, 3, 2, 1, 2, 2, 2, 3, 3, 1, 3, 2, 3, 3. So, if I define a relation R like this, which is 1, 1, 2, 2, 3, 3, 1, 1, 2, 2, 3, 3. So, can I say every element here, it is related to itself? So, that is a reflexive relation. A real life example. Every human being is a friend of the same human being, right? It's quite obvious. It's you versus you, something like that. So, this is a reflexive relation. That is, each element is related to itself. So, we are related to ourselves, right? Symmetric relation. Now, very interesting. A relation R in set A is called a symmetric relation if or whenever, see, if A comma B belongs to R, then B comma A also belongs to R. If that is the condition, then we say it is a symmetric relation. I'll give you a simple example of symmetric relation. Suppose there is a person named Rohan, fine, and I say Rohan is my friend. Rohan is my friend. So I can say that Ashay's friend is Rohan. So can I also say that Rohan's friend is Ashay? Obviously, because if Ashay is a friend of Rohan, it's quite obvious that Rohan is a friend of Ashay. Or else suppose if I have a sister, Sushma, I can say that we are siblings, right? So Ashay and Sushma are siblings. Can I also say Sushma and Ashay are siblings? Yes. So definitely such type of relation is called as symmetric relation, right? It's just like a give and take. It comes back to you. Okay. So here we need to understand the example of the symmetric relation. Suppose we have set A as 1, 2, 3. So a symmetric relation can be expressed as, see, 1, 2, then 2, 1. Ashay Rohan, Rohan Ashay, right? Something like that. 2, 3, 3, 2. So that is an example of symmetric relation. I hope you have understood the example of symmetry. Anyways, you know what symmetry is. You have studied that in your lower grades as well. Okay. Now comes transitive relation. So let us talk about transitive relation. So a relation R in set A is called a transitive relation whenever or if you can say this ordered pair belongs to R and this ordered pair also belongs to R. Then what happens? Then A comma C belongs to R. That is, if A comma B belongs to R and B comma C belongs to R, then we can say that A comma C also belongs to R. Now, I'll give you a simple example. Again, let us take a real life example. Here we have Ashay. Here we have Rohan. Here we have Sushma. Alright. Now, tell me one thing. If I define a relation here that Ashay and Rohan, they are siblings. They are siblings. Then I say that Rohan and Sushma are siblings. Now, can I say if Ashay and Rohan are siblings, Rohan and Sushma are siblings, what is the relation between Ashay and Sushma? They are also going to be siblings. It's very simple, right? So, such type of relation is called as transitive relation. So, generally it occurs between 3 sets. It can be 3 different sets also, set A, set B, set C, right? Similarly here, if A comma B belongs to R, B comma C belongs to R, then A comma C belongs to R, right? So, that is called as the transitive relation. So, suppose if A is 1, 2, 3, so a transitive relation, how can we express that? We can write it like this. 1 is related to 2, observe, 1 is related to 2, 2 is related to 3, and in this particular set, we have 1 is related to 3, correct? 1 is related to 2, 2 is related to 3. Just look at this, you'll get to know. And 1 is related to 3. So, this example is a perfect example of transitive relation. Let's continue. So we can say that if 1 is related to 2 and 2 is related to 3, then 1 is also related to 3. Now this is very important. Equivalence relation. So equivalence relation is what? We'll also have some problems based on equivalence relation. So when is a relation called as equivalence? So equivalence is kind of a perfect relation, that is equal to, because equivalent, equi is equal to, right? So a relation becomes equivalent when the relation is what? Reflexive also, it is symmetric also, it is transitive also. So if all the three conditions are satisfied, we can say that the relation is an equivalence relation. So here, a relation R in set A is called an equivalence relation if it is reflexive, it is symmetric, and it is transitive as well. Correct? So let us have a look at an example. So here you have A, which is 1, 2, 3. Okay, let us forget about the mathematical example. Now here we have a figure for the equivalence relation. Now this cat, can I say this cat is related to herself? Even if I take human being, like I talked about myself, I am related to myself, right? So this cat is related to the same cat. So that is reflexivity. You are related to yourself. A is related to A. Then this cat has some other friend, a different cat, but it comes in the category of cat, right? This is also cat, this is also cat here. So if this is cat 1 and this is cat 2 and they hold a relation, there is a relation between cat 1 and cat 2, then can I say there is a relation between cat 2 and cat 1 also? That is your symmetric. Now again there is a third cat here. So if there is a relation between cat 1 and cat 2 and there is a relation between cat 2 and cat 3, then can I say there is a relation between cat 1 and cat 3? Of course. So this is how the structure looks like, and whenever we have reflexivity, symmetry as well as transitivity, we can say that we have equivalence relation. The relation is called as equivalence. This equal to, we don't write it like this, just to make you understand equi is equal. So such relation becomes a perfect relation, that is equivalent relation. The same example of Rohan, Ashay and Sushma if I take. Ashay is related to Ashay, that is reflexive. Ashay is a brother of Rohan, Rohan is a brother of Ashay. Symmetry. Ashay is a brother of Rohan, Rohan is a brother of Sushma. Then Ashay and Sushma, they are also siblings, right? So Ashay is the brother of Sushma as well. So that's how becomes a transitive, reflexive and symmetric, all three conditions satisfied, it becomes an equivalent relation. Okay. So we have a mathematical example here. We have set A 1, 2, 3. So equivalence relation can be represented like this. Now observe this very carefully. So here I have 1, 1, 2, 2, 3, 3. So can I say this is a reflexive relation? Yes, because every element is related to itself. Go further. Let me talk about symmetric. Now 1 is related to 2 and 2 is related to 1. So if I have 1, 2 and 2, 1, 1, 2 and 2, 1 in a set, right? That will be symmetric, and transitive is what? 1 is related to 2, 2 is related to 3, then 1 is related to 3. So if all the three conditions are satisfied, we can say that it is an equivalence relation. So we need to have 1, 1, 2, 2, 3, 3. Then we need to have 1, 2, 2, 1, right? Then we also need to have 1, 2, then 2, 3, and then 1, 3 for transitive. So if you have all these elements in a set, we can say that it is an equivalence relation. Okay, let's continue. Now comes the new topic. We have understood what relations are. Now let us see what is a function. So let us introduce functions first. So a function is a special kind of relation. It is a special kind of relation where each element of the domain is related to exactly one, very important, exactly one element in the codomain. Each element of the domain is related to exactly one element in the codomain. Let us try to understand this. So a function is defined as f. Relation, we take it as R. Function is given by f from set A to B. From set A to set B is defined as or denoted as See, mathematically we write it like this. F is the function from whom? From A to B, such that f of A is equal to B. F of A is equal to B. We'll get to know this better once we'll have the pictorial format of this as well. So every element in set A, that is whatever elements you have in set A is the domain, is mapped to one and only one, this is very important, one and only one element in set B. I'll give you a simple example. Now, suppose if I am an individual and I come in one set, in one family, alright, I belong to one family and there are two people belonging to some other family, right? So if I have to choose a friend, in this case, I cannot choose two friends. I need to choose only one if I have to call it a function. So I can have multiple friends, right? So that is relation. But when I talk about function, I have to choose one. So generally, a generic thing, a simple example of marriage, right? One person with one person only. So that is realistic example of a function. So relations, your friendships can be many. But when we talk about marriage, right? It's one. Husband and wife, that is the relation. That is a function basically. So yes, in real life we use functions. That's how you can look at things as relations and functions. Okay. So every element in set A is mapped to one and only one element in set B. Now let us have a look at an example. Determine if each relation is a function. Now understand, we have the first example and this is a relation defined, that is 1, 4, 0, 3. So this is your set R actually. And we are supposed to check whether this relation R is actually a function or not. So when it is a function when every element of the first set is mapped to exactly or only one element in the second set. So observe here. So minus 1 is associated with 4. Then 0 is associated with whom? 0 is associated with 3. Then 1 is associated with 5. And then 1 is associated with 7. Now understand. 1 is associated with 5 and 1 is associated with 7. So can I say 1 is associated with 5 also, 7 also? Two different elements. Therefore, this relation is not a function, right? This is not a function because for a function, we need to have only one thing mapped in the other set B, right? So here we have the pictorial representation of it. We have minus 1, 0, 1, 2. We have 3, 4, 7, 1, 5. So minus 1 is mapped to 4. Then 0 is mapped to 3. Then 1 is mapped to 5. And the same one is mapped to 7. So definitely this is not a function. Now let us talk about the second example, that is y is equal to x. Y is equal to x. So tell me one thing, when you keep on changing the values of x, the value of y will keep on changing. Suppose if I take the value of x as 1, y will be 1. If I take the value of x as 2, y will be 2. If I take the value of x as 3, y will be 3. If I take the value of x as 4, y will be 4. So 1 will go with 1 only, no? 1 will be equal to 1 only. It is not going to be equal to 10. This 1 is not going to be equal to 20. 2 will be equal to 2 only. 3 will be equal to 3 only. 4 will be equal to 4 only. In such cases, I can say that y is equal to x. Yes, it is a function. So even if I draw the domain and codomain, so minus 1 goes with minus 1, 0 goes with 0, 1 goes with 1, 2 goes with 2, and so on. You can have multiple examples here. So yes, this is a function. And always remember, y is equal to x is also called as a linear function. It is called as a linear function. We'll not talk much about this. We'll talk that when we see some graphs based on it, but not in this chapter. Okay. So, let us have an example now. Determine if each relation is a function. A simple question. Determine if each relation is a function. So, relation is given here 0, 1, 0, 2, 3, 4. We're supposed to determine whether this is a relation or not. Now, your first values here, these are also called as inputs. So, you put some input and these values are your output. You can look at it like that also, like domain and codomain. So, 0, 1, 0, 2, 0, 3. So, see here, can I say that 0 has two outputs? You can see 0 is mapped with 1 and the same 0 is mapped with 2 as well. So, definitely this is not an example of a function. Simple. So, here it is. This is simple only. 0 is mapped with 1 and 0 is also mapped with 2 and then 3 goes with 4. But because here we have multiple outputs for 0, this is not a function. Okay. So, function is called 1, 1. Now, we are moving on to different types of functions. So, please have a look at this very carefully. 1, 1 and many 1. So, now we are going to focus on what is 1, 1 function. So, a function is called 1, 1. Please make a note of this. 1, 1 means injective. 1, 1 is injective function. So, 1, 1 is injective if different elements in the domain map to different elements in the codomain. Different elements in the domain map to different elements in the codomain. So, here, suppose if I have some elements in set A, say we have 1, 2, 3. I have some elements in set B, say 5, 10, 4, 3. So, if I map 1 with 5, then if I map 2 with 4, and if I map 3 with 10, can I say different elements of set A are mapped with different elements of set B? Yes. So, such type of function is called as injective or 1, 1 function. I hope this is clear. Now, how do we find or try to understand whether it is an injective function without actually drawing this? Now, suppose f is 1, 1 mathematically if all a1, a2 belonging to the first set A. So, if there are two elements, I am assuming them to be different elements. Two elements a1 and a2. But if those two elements have f of a1 is equal to f of a2, that is their images, we call it as image. If the images of a1 and a2 are same, then we will say that a1 and a2, they are also not different, they are also same. Because that is the definition of injective, isn't it? That one person should be mapped with one person. Now, what we have done is, if there are two different images and if both of them are equal, then here also that a1 and a2 are going to be equal. So, the condition says if f of x1 and f of x2, taking it from the codomain, if f of x1 and f of x2 are equal, it implies that x1 and x2 are also equal. They are the same. So, 1 with 1 only, right? Let's continue further. So, function is called many 1. Now, many 1, the name itself is telling many to 1. Many 1. If two or more different elements in the domain are mapped to the same elements in the codomain. We'll have the example of that as well. So, observe this. Here we have minus 4, which is mapped with 16, okay. But if you look at minus 2 and 2, their images are the same, that is 4. So, two of them are having the same image. When this is possible, if you see, can I say if the elements in X are say A and elements in this G of X are B, then the elements are the square here. Minus 4 square is 16. Minus 2 square is 4. 2 square is also 4. So definitely minus 2 square is 4. 2 square is 4. So minus 2 and 2, both of them will be mapped to 4. Although minus 2 has only one image. 2 also has only one image. 4 has two images. 4 and minus 4. They also have one image together. Minus 4, 4 and minus 2, 2. But everyone has individual images, right? So in this case, we can say that this is many 1. So here we'll have many, here we'll have 1. Many 1, many 1, like that. I hope that is clear. But this is a good example of 1, 1, right? So 1 to 1, please make a note. It is called as injective. The other one is many 1. Now let us talk about onto functions. What are onto functions? So function is called onto. Onto function is also called as surjective. Make a note of this. If every element in the codomain, that is the second set, every element in the codomain has at least one pre-image in the domain. Okay. So let us have an example here itself. So f is onto for every b belonging to b, that is b belongs to the second set, there exists at least one a belonging to the first set A such that f of a is b, such that f of a is b. Now understand, notice very carefully, we'll have an example. If you see here, 1 is mapped with 7, 2 is mapped with 9 and 3 is mapped with 8. But this 10 is not mapped to any of the element. That means there exists this 10 belonging to B for which we don't have a pre-image. So such example is an example of non-surjective, that is, there is one extra element here which does not have a pre-image, right? So this is non-surjective. If I don't have 10 here, then this can be an example of a surjective, that is the onto function. I hope this is clear. Now let us talk about into function. So function is called into if there exists at least one element in the codomain that is not the image of any element from the domain. So have a look. We have an example here. So if you see this number 10, correct, this does not have any pre-image here. So we can say that such function is an into function. So one extra is needed. Suppose if we have something like this, say 1, 2, 3, and here we have 5. If everything is mapped, first of all, is this a function? No, it is not a function because 1 is mapped with many here. If I take it like this, now tell me, is it a function? If yes, which type of function? Correct, this is an into function. Why into? Because there exists at least one element in the codomain that is not having any pre-image in the domain, right? So this is an into function. Okay. Now let us talk about bijective. Bijective functions. Bi means two. So it is a combination of two functions. Which two functions? We need to know. Is it, we have studied three functions, right? We have studied about 1, 1, then onto, and then into, right? 1, 1, onto, into. But forget about into. Forget about into. Let's focus on 1, 1 and onto. So a function is called bijective if it is both 1, 1 and onto. So if a function is 1, 1 also and it is onto also, we call the function as a bijective function. This means every element in the domain has a unique image in the codomain, right? Here it is. So this function is bijective because see, This is 1, 1. Every element is having their unique images. This is onto also. Why? Because every element in the codomain is having their corresponding pre-images. There is no extra here. It is not on into. So this is onto also. This is 1, 1 also. So if it is 1, 1, it is onto. It is bijective. See here. Here if you see x and y, the image of x is 1, the image of z is also 1. So can I say here this is not 1, 1. Why it is not bijective? Because it is not 1, 1. This is like many 1, no? Many 1. Correct? This is not bijective because this is into. Right? That is into function and this is not 1, 1. So for bijective, both of them should be clarified. So we can say that bijective functions establish a perfect one-to-one correspondence, right? It is a one-to-one correspondence between the domain and the codomain. So here it is. The same example, of course. I hope you have understood why both of them are not bijective and why this is bijective. Please make a note of this because we are going to have some questions based on this as well. Now, how do we identify whether the function is bijective or not? That also I actually told you. Let's have a quick recap. So step 1 is check for injectivity. Check whether the function is 1, 1. And how do we check whether the function is 1, 1? We start by considering two different sets, set A and set B. So mathematically, we are going to solve it like this. And we will start with this. We'll start with what? Whatever problems we are going to do, we'll start with considering f of x1. That is, we'll start with considering the images to be equal. Equal as in same. Start. So I'm saying start. So start with this. Once you start with this, you solve. And if you get x1 is equal to x2, then you can say that the function is 1, 1, right? But only 1, 1 is enough? No, the function has to be surjective as well. Surjective is onto. That means we want to ensure that no element in set B, none of the elements in the second set is left with any pre-image, that is any connection from set A. So in set B, there should not be an extra element. All those elements should have the pre-image in set A. That is what we are going to check. So here is an example. Consider the function f from R to R defined as f of x is equal to 2x plus 1. The function is given to us. We are supposed to check, is this function bijective? Okay, so what is the condition? We'll check that whether the function is 1, 1 also and onto also. So, firstly, for 1, 1, if you remember, how do we consider? We start with considering the injectivity. That is, we assume f of x1 is equal to f of x2. So here, just put x1 and then you put x2 on the right hand side. So if you solve this further, we'll get like this. 2x1 plus 1. Instead of x, I have put x1 is equal to, for x2, 2x2 plus 1. This 1 will get cancelled, isn't it? 2x1 will be equal to 2x2. 2 will also get cancelled later. And what are you going to get? You are going to get x1 is equal to x2. We got that. We started with f of x1 is equal to f of x2. And then we got x1 is equal to x2. So clearly we can say that this particular function is injective. That is 1, 1 is done. Now let us talk about onto. Whether the function is surjective or not. So for surjectivity, to check whether it is surjective or not, we need to ensure that for any real number y, we can find the corresponding value of x such that 2x plus 1 is equal to y, right? Because we don't have to leave any pre-image in the set B. Okay, so that is nothing but your y here. So y is equal to 2x plus 1. So instead of fx, just write down y. Now what you do is, if you solve this further, get the value of x in terms of y. Get the value of x in terms of y. Firstly, what you did, you started with f of x is equal to y. Then now you find the value of x in terms of y. Now tell me one thing. Can I say for every value of y, you are going to get some value of x? Or are you going to miss anything? No, there is no possibility at all. Because if you put y anything, say 3, you will get 3 minus 1 by 2, 2 by 2 which is 1, you will get x, the value of x as 1. If you put this as 6, 6 minus 1 by 2, 5 by 2. So for every y, you will get some x. That means nothing is missed out. Y is like your set B, imagine. So from there, everywhere you are getting a pre-image, that is x. So if you get something like this, if it was, I'm just giving you an example, 2 upon y minus 1, if it was like this, okay, this is not the problem. Then here, for 1, you won't get a pre-image, right? Because 1 minus 1 is 0 and this will be not defined. So you will not get x. So such type of function will not be an onto function. This won't be surjective. But here, our denominator was 2. So no problem at all. Clearly we can say that this is a surjective function, but this was 1, 1 also. So we can say that this is 1, 1 also and surjective also. So clearly, because it is both, it is a bijective function. Clear? Let's continue. The new topic is composition of functions. That is the combination of functions, you can say. So the composition of two functions f and g is a function that combines them. So f and g are two different functions. Now f is a function on two different sets, g is also a function on two different sets. Then let us see how do we combine f and g together. So f is a function from a to b. So we have set A, we have set B, and g is a function from B to C. So total how many sets are there? 3. We have A, B, C, right? So f is a function from A to B. F is a function from A to B, and g is another function from B to C. Then g of x, we read it as g of x or g of f of x, same thing. It is defined as g of x is g of f of x for all x belonging to the set A. For all x belonging to which set? The first set A. Now here what we do is, the result we apply it on f first here and then apply g to get a new function from A to C. That is from A to B, B to C, then we get A to C. How? We'll get to know in the problems as well. So here is an example. So f is a function defined on set R and fx is given to us, that is 2x plus 3. G is a set from R to R defined by g of x is x square. So fx is given, gx is given. Two functions are given, fx and gx. We are supposed to find out g of f of x. So g of f of x. Now understand this very carefully. G of f of x is written like this. G of fx. Now see here, firstly we solve for f. So what is fx? Fx is this. So g of, instead of fx, you put 2x plus 3. G of fx. Instead of fx, I am putting 2x plus 3. Now what is g of x? See here. g of x is x square. So what you do, g of x, so this entire part, this is your x now, g of x, but g of x is x square. So you have to square this, that is 2x plus 3 the whole square. Expand it using the formula a plus b the whole square. You get 4x square plus 12x plus 9. I hope this is clear. So if you see the previous slide, that is exactly what we said. We solve for fx first, then take g of f of x to get your final answer. I hope this is clear. So similarly, the composition for f of g of x. Now this is different. F of g of x. This was g of f of x. This is called as gof x. This is called as fog x. Yeah, it's actually called as fog x. So this is f of g of x, and f of g of x is f of gx. Now understand, here you have gx, right? So where is gx? Check here. Gx is x square. So instead of gx, write down x square. Now f of x square, correct. So what is f of x? F of x is 2x plus 3. So what will be f of x square? Wherever there is x, put x square. So it will be simply 2x square plus 3. So don't get confused, solve slowly. Firstly solve this part, then go for f of g of x. Solve for g of x, then f of whatever the function is there, and then you'll get the final answer. I hope this is clear. So two things, gof x, fog x. Now if you see this entirely, observe, this was your g of f of x. This was your f of g of x. G of f of x is what? This. F of g of x is what? Are they equal? No, they are not equal, they are different. So always remember, f of g of x and g of f of x, they are not the same. You are not going to get the same things there. They are not equal, right? That is the commutative property here, which does not satisfy. Anyways, let's continue. So f is a function from R to R and g is a function from R to R given by, same thing again, fx is given, see, fx is given sin x, gx is given 5x square. Then find g of f of x. Okay. You write down fx, you write down g of x. Now g of f of x, that is g of fx. G of fx, focus on fx. What is fx? Sin x. So g of sin x. But what is g of x? G of x is 5x square. But this is like your x now. So g of x, sin x. So wherever there is x, you will put sin x. Simple. So you'll get further 5 sin x square, because 5 is there, sin square x, sorry, and sin x the whole square is sin square x. So I hope this is clear to you. This is very simple. Now let us talk about associativity. Associativity in lower grades also you have studied. We always need 3 terms there. Here we are talking about probably 3 different sets. So here the composition of functions is associative if f of a to b is a function and g from b to c is a function and h from c to d is a function, then h of gof is equal to, we'll first take h and g together, of f, that is actually called as gof and hog. You can read it like that as well. So here h and g of f, and here we have h of g and then f. So both of them are equal and the associative property holds true here. So basically if you see, there are 4 different sets. There is a function from set a to b, there is a function from set b to c, and then there is a function from set c to d. Then this condition is satisfied, that is called as associativity. Okay. Commutativity we just saw in the previous slide. It does not exist. They are never equal. Now let us talk about invertible functions. So a function f from a to b is said to be invertible if there exists a function g from b to a. See, the function is from a to b, and if there is a function from b to a, that is from the second set to the first set, such that so f of g of b is equal to b for all b belonging to b, and g of f of a is equal to a for all a belonging to a. This function g is called the inverse of the function f and is denoted by f inverse. So this g is the inverse of f and it is called as f inverse. So basically you can also write it like this, that is f of f inverse of b is b, f of f inverse. Basically f and f inverse, both of them will cancel each other. You don't have to actually cancel that. I'm just telling you for the sake of understanding. Here also same thing is happening, no? G and f, they're inverse, no? In inverse what happens? They're cancelling each other, right? Like if I say 5 and 1 by 5 numbers, they are inverse of each other. They get cancelled, right? And you get 1. Okay, let's continue. So let us have a look at some properties of invertible functions. So function f is invertible if and only if it is bijective. So if a function is bijective, then only it is invertible. Please make a note of this. The inverse of an invertible function is unique. Whenever you take the inverse, that inverse is unique. You are not going to have different answers, different values. One inverse. Only one inverse. The composition of a function and its inverse gives the identity function. That is, identity is like your 1, right? If you recall, identity means 1, right? That is f of f inverse of x is equal to f inverse of f of x, that is x. This is very important. This might be needed for solving problems to check invertibility. Let's continue. So how do we find the inverse of the function? Let us try to understand how do we get the inverse. So to find the inverse of the function, the first step is you replace your f of x with y. Whatever f of x is given to you, you replace that with y. Then you interchange x with y. Then you solve y in terms of x. And then finally, you just have to replace y with f inverse and the inverse is obtained. So I hope these steps are clear. You'll get to know this better once we solve problems. So let us jump into the problems straight away. So here is a question. Find f inverse of 4 if f of x is 2x plus 3. Recall your previous slide. How do we start with? We start by considering f of x as y, right? So let us begin with the solution. So replace f of x with y. So this becomes y is equal to 2x plus 3. Now you solve this further and take x in terms of y. X in terms of y. For that you need to shift 3, y minus 3. Then you need to drag this 2 down. What do you get? You get 2x is equal to y minus 3. So x is y minus 3 by 2. Now recall the next step. I hope you remember that. Correct. Instead of x, we'll write down f inverse of y. See, f of x is y, no? F of x is y. So can I say, if I take it on the other side, f inverse of y will be equal to y minus 3 by 2. So instead of x, I am writing down f inverse of y, right? But we have f of x and we want the inverse of f inverse of x we want. So now you replace this y with x. So what are you going to get? You'll get f inverse of x is equal to x minus 3 by 2. I hope this is clear. And that's it. Because we want f inverse of 4, instead of x, you put 4, you'll get the answer. So let us put 4 there. F inverse of 4 is equal to 4 minus 3 by 2, which is 1 by 2. So 1 by 2, that is f inverse of 4 is 1 by 2. This is the final answer, which is the inverse. I hope this part is clear. Replace, solve, x becomes f inverse of y, then replace x again and you solve it. Okay. So here is a new question. It says, if the function f from R to R is defined as 3x minus 4 is invertible, then find f inverse. Same thing again. A function is invertible is already given to us. We are supposed to find out f inverse. Again, we start by considering f inverse as y, right? So let's continue. We start by considering f of x as y, right? So f of x is y. So y is equal to 3x minus 4. Now we will solve x in terms of y. So shift 4 here, shift 3 down, you get x is equal to y plus 4 by 3. But fx is y. So can I say x is what? F inverse y. So here f inverse y is equal to y plus 4 by 3. But we want f inverse x. So instead of y, you put x now. Now further, instead of y, you put x. So f inverse of x will be x plus 4 by 3. That will be your final answer. I hope this is clear. Now let us have a look at one more example. It says, let f be a function from R to R be defined as fx is equal to 3x plus 2. To find the inverse f inverse, solve y is equal to 3x plus 2. Same thing again, y is equal to 3x plus 2. We replace f of x with y, so y is equal to 3x plus 2. Solve for x, x is equal to y minus 2 by 3. Therefore, the inverse function will be what? F inverse of x will be equal to x minus 2 by 3 because we have already replaced it. Now, how do we come to know whether this is the actual inverse or not? We are going to check this now. F inverse of fx is equal to x or not. If you get f inverse of fx is equal to x, then this is correct, right? So let us solve that. Fx is already given to us. So f inverse of fx. What is fx? Fx is already given, x minus 2 by 3. Given as in we have already solved that. So 3 multiplied by x minus 2 by 3. This will get cancelled. Plus 2 is already here. Instead of x, we have put x minus 2 by 3. Solve this. Finally, you are going to get x only, right? Because minus 2 plus 2 will get cancelled. You can do it in any ways and you get x. And once you get x, you can say that yes, the inverse is correct. The inverse that we solved, which is nothing but x minus 2 by 3 is the inverse of. You also check whether the inverse is correct or not by taking f inverse of fx is equal to x or not. That you need to get. Then only this will hold true. Okay. So let us talk about the binary operations now. So a binary operation is a rule for combining two elements of a set to produce another element of the same set. Let us see how. So if star, you can read it as star, if star is a binary operation on a set A, then for all A comma B belonging to A, the result of A star B is also in A. Now this star is a binary operation. Operations. Binary operation they'll define, but if I talk about generic operations, it can be addition, subtraction, multiplication, division. So as simple as that, if A and B are two elements and A is a set, so A is some big set, and if I have two elements, suppose A is a set of natural numbers, and if A is 2 and B is 3, and if I take this operation as addition, 2 plus 3, that is 5. So can I say 5 also belongs to A? Yes, because 5 is also a natural number. If I take the binary operation as multiplication, the operation is multiplication here, 2 multiplied by 5, 10, that is also a natural number. If I take minus, will minus satisfy the condition? 2 minus 3 is minus 1, but minus 1 is not a natural number, that does not belong to A. So that is how we identify. So basically it is an operation for combining two elements of the set to produce another element that lies in the same set. Okay. So binary operation is denoted as this, where A cross A, from A cross A to A, right? So common binary operations include addition, multiplication, subtraction on the real numbers. So these are very common that we already use, right? So this star can be replaced with plus, minus, into, that depends on the question. So addition on real numbers. Let us talk about the rules of binary operation. So A plus B, is it a binary operation? Yes, A plus B is a binary operation. Since A plus B, it belongs to the set of real numbers, where all A and B belongs to the set of real numbers. So if you take the set of all the real numbers, and if I add any two real numbers, I am going to get a real number. So I can say that A plus B is a binary operation. So multiplication on integers. Let us take one more example. Multiplication on integers. So if I multiply any two integers, can I say multiplication is a binary operation here? Yes, because if I multiply, I am going to get another integer, because integer multiplied by integer is an integer. So that will belong to the set Z. Similarly, please make a note of this. Subtraction on natural numbers. Just now I gave you an example. A minus B, right? So we can say that subtraction on natural numbers is not a binary operation, since A minus B does not belong to, right? It does not belong to natural numbers when A is less than B. If A is smaller than B, that is 2 and 5, you will get minus 3. That is not a natural number. So subtraction is not a binary operation, but where? On the set of natural numbers. So that set is also important. If I talk about real numbers, it is a binary operation. If I talk about natural numbers, it is not a binary operation. Commutativity of binary operations, that is commutative property. So binary operation star on set A is said to be commutative if A star B is equal to B star A. Now that can be like your A plus B is equal to B plus A. That depends on the question again. Let us have a look at an example. So addition on R, that is addition on set of real numbers, is commutative, right? Because if you take any two real numbers, add them like this A plus B, or add them like this B plus A, you're going to get the same answer. So A plus B is equal to B plus A. Simple. Subtraction is not commutative, because if you take any two real numbers, say 3 and 2. So 3 minus 2 is 1. 2 minus 3 is minus 1. They are not equal, right? So not equal. Let us talk about the associativity of binary operations. So binary operation star on a set A is said to be associative if A star B, we'll solve this first, that is A star B star C is equal to A star B star C, where A, B, C, all of them belong to the set A. Again here we can take the example of addition on real numbers. So A, B, C, if they are real numbers, if you add them, the order does not matter, right? A plus B plus C is equal to A plus B plus C. We know this. Subtraction is not associative. That is A minus B minus C is never equal to A minus B minus C. You can take any three real numbers and check. You are not going to get this as equal. Now let us talk about the identity element in binary operations. So an element E, this is a new element E that belongs to set A. So if there is an element E that belongs to set A, it is called an identity element for a binary operation star on A if A star E is equal to E star A is equal to A. That star can be anything. It can be addition, it can be subtraction, it can be multiplication, that depends. So here, if I take an example, addition on R. So if I talk about addition, I have A here and I want A. So what shall be your E? Can I say your E should be 0? Because A plus 0 is A. So here, we can say that 0 is the identity element because A plus 0 is equal to 0 plus A, and that gives you A. Similarly, if I talk about multiplication, can I say 1 is the identity element? Because 1 multiplied by some number gives you the same number. A multiplied by 1 is nothing but 1 multiplied by A, that gives you A. So 1 is the identity element. Where? In multiplication. 0 is the identity element. Where? In addition on R. So this is important. 0 and 1, where we are using that. That is your E here, depending on addition or multiplication. Now let us talk about inverse element in binary operation. So for a binary operation star on set A, an element B belonging to A is called an inverse of A. So B is an inverse of A. Both A and B belong to the set A. If A star B is equal to B star A gives you E, that is the identity element. Now again, that star has to be defined. It can be addition, it can be multiplication, that depends. So E is the identity element of the set A. So addition on R, the inverse of A is minus A. Because when we talk about addition, our E is 0, isn't it? We saw in the previous slide. So when are we going to get 0? When we will add A and minus A. Similarly, can I say the inverse when it comes to multiplication? Of course, for multiplication, we will only talk about non-zero real numbers. 0 does not have any inverse. Please make a note of it. So for multiplication, we need the answer as 1, right? So if I have 5, I need to multiply this with what? 1 by 5, no? To get our E, which is 1. So here, A should be multiplied with 1 by A. So the inverse of A is 1 by A. You can also say that the inverse of 1 by A is A, one and the same thing. Because A multiplied by 1 by A is 1. Now let us talk about the distributive property of binary operations. So a binary operation star on a set A is said to be distributive over another operation. So basically, star is one operation here and this particular dot is another operation. So A star B dot C is equal to A star B dot A star C. Now this star can be addition, this can be subtraction, this can be multiplication, this can be addition. That depends. But they are two different operations. That is why here we have taken star, here we have taken like a dot. So multiplication is distributive over addition. So multiplication here is distributive over addition. That means what? If we take three different numbers, A, B, C, then we know that A multiplied by B plus C, if you solve B plus C and then multiply by A, will give you the same as A multiplied by B plus A multiplied by C. And you know that. You have studied this in your lower grades as well. Now let us have a look at an example. Understand. So star be a binary operation on R defined by A star B. They have given us that A star B gives the result as AB plus 1. A star B is giving us the result as AB plus 1. What operation they have used, we don't know as of now. But the result of that is AB plus 1. We are supposed to show that this operation is neither commutative nor associative. Okay. Firstly, let us focus on commutative. Whether this is commutative or not. So for commutativity, what do we check? We check that A star B should be equal to B star A, right? If A star B is equal to B star A, we can say that it is commutative. So for commutativity, firstly A star B is given to us. A star B is AB plus 1. Now if A star B is AB plus 1, if I reverse this, if I take B star A, can I say this will be BA plus 1? Correct? Now tell me one thing. Can I say AB and BA are equal? AB and BA means what? Product of two numbers. 5 multiplied by 2, 10. 2 multiplied by 5, 10. Right? 2 multiplied by 3, 6. 3 multiplied by 2, 6. So AB and BA, both of them will be equal. So can I say here that A star B is equal to B star A? So definitely this is commutative. So let me just change the question. So we are supposed to show that this operation is, we cannot say neither because commutative definitely it is there, but associative we don't know. Let us check. So for associativity, we need A star B star C is equal to A star B star C. So let us solve for A star B. It is given, A star B is already there, AB plus 1 star C. Now this is like your entire, you can take it like your A. So A star C will be AC plus 1, right? That is AC plus 1. So this is A, this is A. I hope this is clear to you. Just solve that. Now let us take the other one, that is A star B star C. So firstly B star C will be BC plus 1 and then A star BC plus 1, that is, this is like your B now, A star B. So that is AB, A, B plus 1. So you solve this further and you can see that both of them are not equal, right? Since they are not equal, this is not associative. So we can reframe the question, we can say that definitely this is commutative, but this is not associative. I hope this is clear. Now let us have a look at a question based on equivalence relation. The question says, let A be a set of 3 numbers 1, 2, 3 and a relation is defined on set A as R is 1, 1, 2, 2, 3, 3, 1, 2 and 2, 1. We are supposed to prove that R is an equivalence relation. Relation, this is a question based on relation. So if you remember, equivalence relation we get when the relation is reflexive, symmetric and transitive. All 3 of the conditions must be satisfied. So let us have a look at this. So a relation is an equivalence relation if it is reflexive, symmetric and transitive. So let us talk about the reflexivity. Now observe, we have 1, 1, 2, 2, 3, 3, 1, 1, 2, 2, 3, 3. That itself is reflexive, right? That is, every element is related to itself. 1 is related to 1, 2 is related to 2, 3 is related to 3. So yes, reflexive it is there. Let us talk about symmetric. For symmetry what we need? 1 to 2, 1, right? So let us check that. So for symmetry we check that if A and B belong to A and if AB belong to R, then B comma A also belongs to R. So we are supposed to check where A comma B and B comma A, both of them are belonging to R or not. So if you see, have a look at this, 1, 2 and 2, 1. You can see here 1, 2 and 2, 1. Both of them are there in R. So clearly we can say that this particular relation is symmetric as well. And what about transitive? For transitivity what do we check? We check that for all ABC belonging to R, if A comma B belongs to R and B comma C belongs to R, then A comma C belongs to R. That means if A is related to B and B is related to C, then A is related to C. So that is what we check in transitivity. So we need to check all the possible combinations of AB and BC. So check the combinations of AB and BC here. We have 1, 2, but we don't have 2, 3, we don't have 1, 3. So basically this is not a transitive relation. So R is not an equivalence relation. R is definitely reflexive, R is definitely symmetric, but R is non-transitive. So the statement could have been different. Check whether, instead of prove that, we can say check whether R is an equivalence relation. I hope this is clear. Now let us see a problem based on inverse. Find the inverse of the function f from R to R such that fx is equal to 2x plus 3 by 5. So we know the procedure, right? We will consider fx as y. Then we solve for x. That is, solve for x as in, we put y, then find x in terms of y. So here we go. We will find x in terms of y. But we know that fx is y. We know that fx is y, right? What will be x? X is f inverse of y. So we say f inverse y is equal to how much? 5y by 3. sorry, 5y minus 3 by 2, and then replace y with x. So f inverse x is equal to 5x minus 3 by 2, and 5x minus 3 by 2 is the final answer. Now let us see one more question. It says, let f be a function from R to R such that fx is equal to 2x minus 1 and gx is given as x square. Find g of x, that is g of f of x. So firstly, we know that g of f of x is g of fx. What is fx? Fx is already given. Fx is 2x minus 1. So put it there, right? So you get g of fx, that is g of 2x minus 1. So this will be like your x now. But what is g of x? G of x is x square. So instead of x, put 2x minus 1. So you get 2x minus 1 the whole square. Expand it, you get 4x square minus 4x plus 1. So that is your g of f of x, that is g of x. Now is an interesting question. Prove that the function f from R to R, fx is equal to 3x plus 4 is both 1, 1 and on 2. It is 1, 1 also, on 2 also. Basically, it is a bijective function. That is what we are supposed to prove. So firstly, to prove 1, 1, if you remember, we consider x1 is equal to f of x1 is equal to f of x2. So here also for 1, 1, let us consider f of x1 is equal to f of x2. So instead of x, put x1, instead of x, put x2 on the right hand side. Here, you get 3x1 plus 4 is equal to 3x2 plus 4. You solve this now. How do we solve this? This will get cancelled, right? 3, 3 will also get cancelled. And finally, you will get x1 is equal to x2. Once you get x1 is equal to x2, you can say that this function is 1, 1. Now, how do you prove onto function? That means we are supposed to find out that all the elements in the second set should have the pre-image in the first set. So for that, you can consider f of x is equal to y, right? So fx is equal to y we are going to consider, where y belongs to R because obviously y has to belong to R. Now, so y will be equal to 3x plus 4. Solve for x. What will be x? X is equal to y minus 4 by 3. So can I say for every value of y, you are going to get some value of x? Yes. Therefore, this is definitely an onto function. Correct? So, it's onto also, it's 1, 1 also. So we can say that it is a bijective function. Now we have a new question. It says, let a be r minus 1. So we have to exclude 1 from the set of real numbers. And then x minus y, that belongs to r, right? Which is given as x minus y by xy minus 1. So firstly, we are supposed to prove that r is an equivalence relation. That is, it is reflexive, symmetric and transitive. So to prove it is equivalent, obviously we'll prove it is reflexive, symmetric and transitive. So firstly, every element is related to itself. So x is equal to y. So instead of y, put x. X should be equal to y, right? So if we put that, we are going to get 0, which belongs to the set of R, right? So we can say that this is reflexive. For symmetric, what are we going to do? We'll solve this. This implies x is equal to y. So if x is equal to y, see, if I solve this, that is if I put it here, I'll get x minus y is equal to 0. And then shift y on the right hand side, I get x is equal to y. So if x is equal to y, can I say y is equal to x? X is equal to y is equal to x, same thing. So this is symmetric, right? Now what about transitive? Now for transitivity, what do we need? We need ordered pair x comma y belonging to R. We need ordered pair y comma z belonging to R. Then x comma y and y comma z, both of them if they are equal, we can say that x is equal to z. This implies x is equal to z, right? So we need to check x comma y and y comma z are equal. But if you remember, x is equal to y we have already proved. Similarly, for this, can I say y and z will be equal? If you just replace x and y with y and z, if you replace this x and y with y and z and then equate it with 0, you get y is equal to z. So yes, x is equal to y is equal to z. Can I come to a conclusion that x is equal to z? Yes. So we can say that this is transitive. So it is reflexive, symmetric, transitive. Therefore, it is an equivalence relation. Now here is the question. It says fx is equal to 2x plus 1 and gx is equal to x square. We are supposed to find out g of x and fog x. It's a simple question. So for g of x, we already know it is g of f of x. Put fx, that is 2x plus 1. G of f of x, g of 2x plus 1. But g of x is x square. So we get 2x plus 1 the whole square. Expand the bracket, you'll get it. And finally, f of g of x. That is f of g of x. Put g of x is x square. Will come here, f of x square. So instead of x, put x square. You get 2x square plus 1. So that's all for today. I hope you enjoyed the session. We learned about relations and functions. We are going to continue this series and see some other chapters as well. See you. Thank you.